What you see is a sketch of the pinhole camera model. As you probably can recognize, this sketch is rather old because the pinhole geometry is used since at least the 17th century, and it was first introduced as a drawing aid. So some guy was sitting in this black chamber and drawing on the back wall, and this helped him capturing the real world outside. And this is exactly what we want to do as well. This model is rather simple. It only consists of this black chamber, which has a hole on it outside at one side, and then rays of light from the outside travel through this hole and are projected on the back facing wall of the chamber. So what we want to do is to capture the travel of light, which is sketched out here mathematically, or more formally on the next slide. For this we define a function p, which is like shorthand for projection, which takes a 3D point big P and maps it to a 2D point small p. So this is the world point outside, and this is a point on the back facing wall of the dark chamber. Here again, which components this points consist of. So this is a 3D point, this is 2D point. And then the function also has some other parameters like R, T, and C. And these are typically the ones we want to derive during calibration. Notably, C are the calibration parameters, and R and T are the position of the camera in the world. R is for rotation and T is for translation. And together these two parameters are called the extrinsic parameters because they are like outside of the camera. It's like the position of the camera in the world, so it's not inside the black chamber. Yeah, here it goes again. We have T, the translation, and R, the rotation. And typically the direction this is describing is world to camera. So against intuition, the camera is always at the origin and the world moves around the camera. So this is easier to, it will be easier later on. One thing to note here is the rotation. It says it's a 3D rotation, but typically we describe the rotation by a 3x3 matrix. And now you can wonder how does this fit, because the 3x3 matrix has 9 entries and thus 9 degrees of freedom. But our rotation only has 3 degrees of freedom. This means that the matrix needs to be restricted such that although it has 9 entries, there are only 3 degrees of freedom. So to this end, the matrix, or first we require the matrix to be orthogonal. This means that the inverse of the matrix is simply its transpose. So yeah, this is what this says. And a consequence of these is that we now only have the upper triangular part of the matrix, which is free, because the lower triangular matrix is coupled by this relation. This relation is equally to the determinant squared of the matrix being 1. However, this is still not enough to arrive at only 3 degrees of freedom, because the upper triangular matrix still has 4 entries. And the way we further restrict this is by requiring the matrix to be special. Special means that the determinant is strictly +1 and not -1, which is still allowed here. And together these two requirements form a group which is called special orthogonal group. And because we are talking about 3x3 matrices, it's special orthogonal group of 3. And yeah, now we arrived at a 3x3 matrix which only has 3 degrees of freedom. A particularly useful test is to check always check this if you encounter a rotation matrix, that its determinant is +1. If it's not, it is not a rotation matrix. It might involve some mirroring and shearing and things you do not expect. So if working with linear geometry something goes wrong, always check that you actually have a rotation matrix. Furthermore, there's another way to express a rotation besides the matrix. It is the Rodriguez vector, which conveniently only consists of 3 entries, and therefore it's a Rodriguez vector. You don't need any more checks, and it's the most compact representation of the rotation. There's also quaternions, but we skip them here. We mentioned the Rodriguez vector here because it's like the typical rotation representation in the OpenCV library. And you can always convert a Rodriguez vector back to a 3x3 matrix, or you can go also from a 3x3 matrix to the Rodriguez representation. And yeah, you can use the Rodriguez vector where you have lots of rotations, because it's like only 1/3 of storage compared to the matrix. Also, if you want to have the derivative of a rotation, use the Rodriguez vector, because with the matrix it's not straightforward, but here it is. Okay, now that we know what rotation and what a translation is, let's take a look how to actually apply such a transformation. This means we have given a point in world coordinate space, and we want to transform it back to the camera coordinate space. Again, remember that the camera is assumed to be at origin. This is done as following. First we apply the rotation to the point, and then we apply the translation. However, this is slightly cumbersome, because you always have to remember whether you first add the translation vector or you first do the rotation. Like, it's pretty clear, because dot has a higher precedence than plus, but nevertheless, there's slightly simpler or more straightforward representation of the transform, namely homogeneous coordinates. For this, we extend our world point by the homogeneous coordinate w, and we set it to 1. And now we can express the whole transform as a single matrix vector multiplication. For this, we build a matrix of dimensionality 4x4, and the upper left corner is the 3x3 rotation, and then we add the translation to the right. And for the bottom row, we have 3 zeros and then the coordinate 1. And if you use this matrix, it exactly does the same like the above. It first applies the rotation and then the translation. Okay, so now that we know how to go from world to camera, let's talk about the reverse direction. Now we have a 3D point in camera coordinate space, and we want to get the according coordinates in world coordinate space. So this means we need to go the reverse direction. If you recall, we first applied rotation and then translation, and so we have to do this here accordingly. We first invert the rotation, like here. Recall that the inverse of a rotation is just a transpose of it, and after we inverted the rotation, we can remove the translation. This is now slightly more complicated formula, and when we are using homogeneous coordinates, like here, it is slightly more convenient. Of the inverted matrix, it already did this thing and rotated the translation direction. However, keep in mind that the inversion is a much more involved operation than this one, and if you are in a performance sensitive area, you should always do this because it's faster than doing a 4x4 inversion. Okay, now that we have covered the extrinsic parameters, let's turn to the intrinsic parameters of the camera. For this, let's take a look at this pinhole representation again, and this time we have a 2D schematic view of everything. The first thing to note about this sketch is that we flipped the back wall from here to the front because it makes discussion slightly easier. And now we want to derive the mathematical equation of the ray. The ray is this red line in here, and it connects any 3D world point in camera coordinate space, like here, to the origin of the camera coordinate system. And while traveling along this ray, at some point we intersect with the image plane, like here. This is exactly the same, like if the image plane would be behind the camera origin, then it would be intersecting somewhere here. So in this image we have some additional geometrical properties, namely we have the width and the height of the image plane. These are typically measured in pixels. And if we intersect the ray with the image plane, we get an intersection point UV, and it's typically also in pixel coordinates. Then we also have this thing here called principal point, but we will discuss it only on the next slide because then it's slightly more obvious what it does. Okay, so I'll turn to the next slide. Here, this is again the same geometry like in the previous image, but we are looking on it from the side. So this simplifies the discussion a little bit because we only have a two-dimensional space here, and hence the x component of the world point is dropped. So what we want to derive here is given some world coordinates y, z, the image coordinates small y, f. And what we are going to use here is the intercept theorem, which basically relates this vector in blue here and the distance to origin with this small vector in blue with this distance. And this distance is z, the distance of the point to the camera origin. And this distance is f, and it's the distance of the image plane from the camera origin. Note that we again use the same schematic like initially with this old sketch, where the image plane is behind the camera origin. Okay, so the relation is y derived by z is small y derived by f, and we are interested in small y, so we modify the equation like this. And yeah, basically we could be done here, but we also add this principal point cy. So why do we do this? Because the image plane, which is like this dashed gray line here, does not have to be aligned with the optical axis like this one. And it's also not done in this example, where the center of the image plane is here, and therefore we have like this offset cy between the optical axis and the center of the image plane. And to compensate for this, this is why we add the principal point or the cy offset here to move the coordinate to the image coordinate system. So this point is still in the camera space, and when we add the principal point, we are now in image space, like in pixels finally. Yeah, and this discussion allows to assemble our final camera model, which we do in the next slide. So this is the final camera equation. And as we typically do with matrix notation, we read it from right to left. And here we have the 3D world point P. Then we have the rotation and translation. The brackets indicate that we somehow apply it to the P, like you can think about the 4x4 matrix here. And now we have our intrinsic matrix K. This basically encodes the intercept theorem from the last slide. Notably, we pulled out the Z division beforehand. This means that the points which you multiply with this matrix already are divided by Z, and the components are X by Z, Y by Z, and then Z by Z, which is 1. And what this means, if you take at the X component here, that we multiply Fx by X divided by Z, and then we add the principal point Cx. And if I now go back one slide, this is exactly what we did with Y here. So imagine we are talking about X. Now it's Fx by X divided by Z plus Cx. This would be this row, and for Y it's like exactly what you've seen on the last slide. So this equation allows us converting 3D world points into 2D image coordinates in pixels. And it's really important that you fully understand this equation, because it will be the basic for the rest of the content we are discussing in this lecture. For this, I recommend you to go at this web address where you can interactively play with each individual parameters and see what effect they have on the final image. One more note, if you read up the K matrix somewhere else, you might encounter one more parameter, namely this Q. It will be here, and it is force set or fixed to 1 in our model, because we are mainly talking about CCD digital sensors. What this Q parameter models is is when your pixels are not do not have a right angle, but rather have some skew. This could happen with film cameras, where the film is deformable, but CCD sensors are rather sturdy, so it's safe to assume that skew is 0. And this is why we are ignoring it. Also, the OpenCV library does not allow you to calibrate this skew with the basic camera model. You might wonder, yeah, this is all nice, but does it model the real world? Does this actually work? And yes, we can already build a camera like this. It will look something like what you see here. We basically punched a hole in the camera cap, which is our pinhole. And there's also a small community which does photos like this. And they look something like what you see here. So if we take a look at the photo, we already recognize, okay, this is the real world. We see what was photographed, but we also see some bad things about using pinhole in real life. First of all, the image is rather blurry. And next, the image is also a little bit too dark. So what is the issue? It's the size of the pinhole. If you make it too large, then things start to become blurry, because more than one ray of light hits the image at 1 pixel. But also, if you make the hole too small, then not enough light hits the image sensor and the image becomes dark. So it's always a compromise between a too dark image and a too blurry image. And this is like one compromise which you see here.